Have you ever stopped to wonder how a car company can promise a certain gas mileage? Or how an engineer can design a bridge to stand strong against forces they can't even predict? Well, the truth is, our entire modern world is built on managing something that's all around us, all the time: variability.
Just think about it for a second. The mileage you get in your car, it changes with every single trip. The actual strength of a copper wire, it's not perfectly identical from 1 inch to the next. Every single product, every process, every system has this randomness kind of built right in, what engineers like to call noise.
So you can see how this creates a huge challenge, right? If everything is always a little bit different, how on earth can we design things to be reliable? How do we solve really complex problems and actually feel confident in our answers? We need a way to cut through all that noise, to find the signal hidden inside.
And that is exactly where this amazing field comes into play. See, statistics isn't just about boring charts and numbers you learned in school. It's literally the toolbox for understanding and navigating our variable world. It's the science of data.
Okay, so the very first tool we got to pull out of our box is a way to talk about all of this randomness. We can't just wave our hands and say something is kind of risky or pretty likely. No, we need a precise language. And that language, my friends, is probability.
What probability does is it lets us take this fuzzy, vague concept of chance and pin a specific number on it, usually somewhere between 0 and 1. It gives us the power to actually measure and compare how likely different things are to happen. Basically, it's how we turn our gut feelings into solid, hard data.
And here's where that idea gets super practical. Let's say you're in manufacturing. With probability, we can calculate that a part with some surface flaws has a 25% chance of being defective, while a part that looks perfect has only a 5% chance. Now that's not a guess. That is a calculated risk that helps people make absolutely crucial decisions right there on the factory floor.
So once we can get a handle on the chance of a single event, the next step is to start looking for hidden connections between different things. This is where we level up from just describing the world to actually predicting what's going to happen next by building models from our data.
Now I know an equation like this might look a little intimidating at first. All those Greek letters, I get it, but don't worry about the symbols. This is a statistical model, and I want you to think of it less like complicated math and more like a recipe or maybe a map that connects a few ingredients, our inputs, to one single predictable result. In this specific case, it's a map for predicting how strong a tiny wire bond inside a semiconductor is. The model tells us, hey, the strength really depends on the wire's length and something called the die height, which is basically just how tall the little chip is. By using a model like this, we can figure out which factors truly matter in a really complex system. And really, it's as simple as this. That big equation works just like a machine. You feed it the info you have, like the wire length and die height, and it uses the rules it learned from all the past data to spit out a specific, data-driven prediction for that pulse strength. It literally uses what you know to predict what you don't. How cool is that?
All right, so we can quantify uncertainty, we can build models to predict things. But what happens when we just need to make a clear choice between two different options? Well, that brings us to our third core tool, a formal way to make decisions with data, and it's called hypothesis testing.
So imagine you're a chemical engineer. Someone comes to you with a brand new catalyst that's supposed to make your process way better. A hypothesis test forces you to set up two competing ideas. The first, the null hypothesis, basically assumes the status quo, that the new stuff is no different than the old stuff. But the alternative hypothesis claims that yes, there is a meaningful difference. The whole point is to see if our data gives us enough proof to confidently reject that nothing has changed idea. Okay, so we run our experiment, we collect all the data on the chemical yield from both catalysts, and the results are in. The average yield for the new catalyst is a little bit higher. But here's the million-dollar question. Is that tiny difference a real improvement, or is it just that random noise we were talking about at the very beginning? To get our answer, it all comes down to this one single powerful number, the p-value. The p-value tells us the exact probability of seeing a difference this big, or even bigger, if, in reality, the new catalyst was actually no better than the old one.
In this case, our p-value is 0.73. That's really high. It means there's a 73% chance we'd see a result like this just because of random luck. So what's the bottom line? The data gives us absolutely no strong evidence to justify switching. We just use statistics to avoid making a very costly and ultimately pointless change to the process.
So those three tools, probability, modeling, and hypothesis testing, they are the bedrock, the foundation of the whole thing.
But of course, the story doesn't end there. As data gets bigger and our problems get way more complex, the toolbox is constantly growing and evolving.
We are now moving into an era of incredibly advanced methods, designed specifically to handle the massive, sprawling datasets of the modern world. Fields like applied statistics and other areas of mathematics are giving us these powerful new techniques to solve entirely new kinds of problems.
Take computational linear algebra, for example. I promise, this is not your high school algebra class. This is the heavy-duty mathematical engine that powers so much of today's machine learning and data science. It gives us the tools to work with data that has hundreds, even thousands of dimensions, stuff that a simple spreadsheet can't even begin to handle.
And then you get to equations that look like this. This is called a stochastic differential equation. We don't need to break down the math here, not at all. But just looking at it tells you we're dealing with a very sophisticated language. It was invented to model systems that change randomly over time, like the price of a stock or the movement of particles in a liquid. It's really a glimpse at the cutting edge. So, from figuring out the chance of a defect, to predicting the strength of a wire, to deciding if a new idea is actually worth it, this amazing toolbox helps us make sense of a messy, variable world. And it leaves us with one final thought. What problem in your world, what noise in your work or your life, could be turned into a clear signal if you just had the right tool from the box?